I started a recording. Yeah. Can you repeat your question for the recording?
So like in the previous lecture, like there was a circle which was centered at the origin and some concentric circles. So can you explain that graph once again between W0 and W1, like parameters?
So,
It was there in the regularization.
right, I get it. So you said that there's, can you see this drawing on the W0?
Yes.
So you said that there is a graph between W0. So this is a point. That's what you want to know. What is this point? Huh?
No, like there was a circle centered on that point origin, and there were some concentric
Right.
circles which were there over there, and they were intersecting. So
Okay, fine. So this is for the error function, these circles, right? So this is like, this is for error function, EW, right? So it is like a sum of square error, which is because of the likelihood function. So if you remember, we had two terms, right? Sum of square error plus regularizer, lambda W transpose W.
yes.
So this is for W transpose W at the origin. And this second is one is for likelihood. So if you remove the second term W transpose W, which is with the lambda, so then you left with only the sum of square error, which is nothing but the result which you will get is the likelihood result, right? So if you minimize that error, likelihood error, you will get somewhere this W, right? So this W is nothing but a likelihood solution. Is this making sense to you?
So like in the book, in that origin, there was only one circle, like not concentric circles. So like it was like,
Right. So there are
yeah,
so many levels. So there can be so many level curves, right? So just for the simplicity in book, they have said that they have shown only one level curve. So if it is like up, if you just visualize this kind of form in 3D, right? So it is a 3D structure, right? So if you cut from here, you cut from here, you cut from here. So from in the different heights, and you draw it into a plane, so it will give you this level curve. So this will cut, this is a circle, right? So this is a circle here. So if you draw it here on the 2 dimension, this give you this circle. So when you cut this surface here at that time, it will give you this level curve. So when you draw in 2 dimension, it will give you this circle, right? Similarly, at different heights, you will cut it, you will get a circle because it's a 3D structure. Can you see this is a 3D structure here, right? So if you cut
yes.
it here, so it will some circle. So when you cut it at different height, you will get different circles, right? So when you plot it, it will give you different level curves. So in book, they have just shown only one level curve. But if you want if you just cut it at different levels, so you will find out like there are different there's concentric circles. So I
So
said
like,
that this is
yeah, why they intersect with each other? Like we showed a special point, right? Intersection between these
right,
two.
right. So now this error curve is over like whole space from W on W0, W1, right? So it is over whole space. So it means if this is a line here, so I'm talking about only error curve. So let's say first see only likelihood function. So this is a likelihood function. So if likelihood is a function, it may seems like this, right? Right? In 2 dimension, it is a curve. It is a
Yes.
surface, like parabolic surface, right? So it may seems like this. And it is for every value of W, for every value of W0, W1, there is a point somewhere on the surface, right?
Yes, sir.
So So now there are infinite W0, W1 on this 2 dimension plane. So now if I have infinite, so therefore every point there will be a corresponding point on a surface, which is this, right? This surface.
Yes, sir.
So it means this surface is all over the plane, right?
Yeah.
So now if you cut it from 0 to infinity, it means you find a concentric circle all over the plane, right?
Yeah. Yeah.
This concentric, right? So just for simplicity, I don't want to just do figure dirty. So I just can avoid these concentric circle, outer concentric circles. So just I'm restricting myself to some level height, some specific height. And that specific height will give me some specific concentric circles, right? So I just to for make my figure clean and clear, I have just restricted my surface height to this curve level, and this is why I'm getting a level curves because of the likelihood curvature, because of sum of square error, and it is touching this point is showing the minimum. This is point is showing the minimum of this surface, right? This surface. So in 3D, you can see this surface as like this.
Okay,
Is
so
it making?
like there will be a plane, no? At minimum point, you can draw plane.
No, no, it will be just a point, right? It will be a tip. It will be a
Ah,
pit tip. So
yeah.
if it is surface, so if you cut it from here, so what it will be? It will be just a point, right? It will be just a point which you are drawing here. So this is just a point,
Yeah,
right?
yeah.
So now so this is there are so many level curves for likelihood function. If you minimize your likelihood function, the solution that you will get is this point. Fine.
Yes, sir.
But I said that you need to restrict your W0, W1 to this circle only. Fine.
So when restricting, is that radius fixed or like we are restricting the radius?
No, it depends upon lambda, what lambda you are taking. If lambda is infinity, this radius is zero.
Okay.
Fine. So now if I say that there is some specific lambda which result into this circle, it means I want to find out a value of, I want to find out a value W, which will minimize my error function. So which will minimize my error function. So the level curve which is touching this circle somewhere tangentially here. So this is that W, right? Because I want to do a constraint problem which where I want to restrict myself into this circle, but I want to minimize my error also. So I will take the maximum liberty of my constraint. I will go to the boundary, because why I want to move toward boundary, because moving towards the boundary will minimize my error function, because the error is somewhere minimum at this point, right, which is outside the circle. So to achieve the minimum in the constraint, you have to go to the boundary, and this boundary is touching tangentially to the level curve of the likelihood function. So you will get somewhere this is a minimum, right? Is this
Okay.
intuitively
So
making sense, guys?
yeah, yeah. So if we increase the radius, then we are more likely to get that minimum point in
Exactly. So
the.
if you just so if you go to lambda equals to zero, it means if lambda is zero, then you are not at all putting any constant, and there will be a bigger constant which will cover this minimum point of likelihood function, and hence it will be inside the constant, and you will say that okay, I got it. I got the minimum of error function because I am not at all using my constant. It means I can go to any value of W. So my level curves go to the infinity.
Got it.
Fine. Anybody else having any other confusion regarding this? Right. So if it's a good question, and I hope that those who have listened this may have get a more clarification on it. The other thing is like yesterday, one of the student was I don't remember the name, but he was saying like uh, I was doing something U lambda U transpose, and then I did just inverse. Then I said you just take the diagonal value inverted, right? So this is lambda 1, lambda 2 diagonally, and it will give you the same result. So I hope that you have clarified that thing on your own, right? And if not, you please go and just read it again. Okay, so let's start this today's class. So before that, I want to just have a quick recap. Like for maximum likelihood estimation, we said that we can say understand it geometrically. To say that this is my design matrix where every column will be like defined by a basis function. So these are my basis function. All these basis function will span a space. That space is known as a space, let's say. So you cannot go if you want to take a linear combination with help of some W, right? Then you will be in this plane, right? So you will be in this space S. So when you take a linear combination, let's say you are getting this Y. Now this Y cannot be never be T because T is not in the column space of the design matrix. So you want to minimize the error so that Y should be as close as to T possible. This can only happen when you have an orthogonal projection, or means there is a minimum distance between Y and T. So we have just discussed in detail, and you just refer to this previous recording in case of any confusion. And we found out that this is nothing but least square giving the orthogonal projection solution. Fine. Then we came with the regularized terms and found out that as we have discussed in detail, this is my likelihood term and these are the constraints which I am putting on my parametric space, and I found out that this is the solution which I am going to get it, right? And this solution is nothing but it is like this is a constraint circle and this is a likelihood circle, and the where they are touching tangentially, this is this value, right? Then I showed you like how to derive this. So this was my likelihood term, and this is my regularized term. I just have taken a derivative with respect to W, and once I do some matrix calculations, so I found out that putting it equals to 0 will give me the minimum of it, right? Where both terms can be sequentially minimized. So it shows me that W can be minimized when I have this solution. When I put this W equals to this, so this error function will be minimized, right? So if you put the value of W, lambda I plus the phi transpose phi inverse phi transpose T, then these two terms collectively will be minimized, right? And you will have a unique solution because my sum of square it is a quadratic function, my constant is a quadratic function, so both are quadratic terms. You can have an analytical solution which will give you a unique solution, right? Then we said that not only L2 regularizer, you can go for L1 regularizer, and here this is a L1 regularizer. Now what will happen? You will have a likelihood function which is having a concentric circle like this. So solution for likelihood function is this. But now you have put a constant. The constant is somewhere rhombus, right? So you just increase the when you just try to find out where it both collectively will be minimized. So the probability is very high. So please remember this term. The probability is very high that they will cut to near to the edges, right? If they It is not always possible that they cut to the edges, and sometimes they cut on to somewhere here. So in that case, your sparse solution will not be there. So then what you have to do, you have to rotate these axes. When you rotate these axes, what will happen? So then here this rhombus will be somewhere like this after rotating it, and then it will cut somewhere here. And because of this W0, W1 you have rotated it, it will again get a sparse solution. So this is again, I said that it is Huy's theory. So we will somewhere, if we get a time, we will discuss it. But the point to bring this here is that the only not only we have L2 regularizer, but in general we can have Q, right? And Q can have any value from like 0 to infinity, right? So there is L2 norm, infinity
So,
norm, and
so like in
yes,
sparse solution, we have any weights become zero, right? Some of the weights become zero, no? So
right, right.
can you explain that here diagrammatically what you have done? Like you have drawn a tangent, no? A common point.
Right, right. So
So
assume
how
that
is
just
W0,
to
W1
intuitively,
becoming
let's
zero?
say this is what you have a no, right, not see here. So this is a constant here, right? So you need to find out the value of W within this rhombus, right? Now this is your likelihood function. There are the level curves here. So these level curves somewhere will cut automatically here, and this will be the point because this point is having zero value on W0 axis. So this will be having a sparse solution. So it's not very straight to tell, right? So it takes it intuitively it makes sense, but if you want me to derive it, it will not
Yeah,
that
no,
much.
so got it.
Fine. Okay. So then this is what already we have discussed it. Then I ask you to just go through this, and if this line doesn't make sense to you, so then you need a discussion with your friends and colleagues. And if it still doesn't make sense, you can ask a clarification to me. But I have already told you in first three lectures what does this line mean, right? So regularization allows complex models to train on a data set of limited size without severe overfitting, essentially by limiting the effective model complexity, right? Okay, then we were discussing a Bayesian linear regression, which is the topic for today's class. And I just want you to get very deep into this discussion, and so that it makes a sense to you. So first, as I told in my last class, there are two spaces, right? One is a parametric space. So parametric space that let's say I just for simplicity, I'm fixing that I am fitting a line to my data set, right? So if I'm fitting a line to my data set, so there are my parametric spaces of two dimension, because line is having two parameters. One is intercept, which is I'm saying by W0, and a slope, which is I'm showing by W1, right? So if there is a point, it is a line. This is a parametric space. The other is if I take this line, and I draw this line, so I need to go to a functional space. So now I have a X here and I have a Y here. So if I take this line, so it is having this intercept, which is let's say 1, and this is slope that is also 1. So I am just cutting, I am drawing a line here. So for this point, I am drawing a line, right? So this is, I am doing in a functional space. So this is my functional space and this is my parametric space theta, right? So there are two different spaces. So here what I have shown, this column is showing as a functional space, and this column is showing you a parametric space. Even this column is also showing you a parametric space. Fine. If this is, then what I have said, like because this is a parametric space, and I can, every point is a line here, and I have not seen any data so far. So if I have not seen any data and you came to me and tell me like, what do you think, which model is the best model, right? So I need to choose among infinite lines. I need to choose one of the line. So for that, I need to define some distribution to pick that point, to pick that line, because point is a line here in this parametric space. So what I'm doing, I'm just defining a distribution over this parametric space. And for simplicity, this distribution is nothing but it's a normal distribution where identity matrix is, where covariance matrix is identity. It means I will get a concentric circle, right? So now if you ask me to choose a line, so I will pick a line with a maximum point with a maximum probability, and this is nothing but 0 intercept and 0 slope. If you draw it in a functional space, what will happen? It will just go over the x-axis, because x-axis have a 0 slope and 0 intercept, right?
So why is the value of that W0 and W1 between -1 and 1 only?
And just to draw it pictorially, right? Because it is a Gaussian. If you know 90% of the Gaussian will fall into the probability of 90% Gaussian fall between 2 standard deviation or 3 standard deviation, right? So this is like after that, the probability of getting any point is 0. You don't know what is Gaussian distribution, I hope, right? This is a Gaussian distribution. So the probability after a certain time, range will be 0. So I don't need to consider all those points which are having a probability 0 here, right? So this is red is showing the high probability, and this yellow is showing a bit less probability, and this is a faded probability, and finally this blue is showing the 0 probability here. So it is the way to draw a three-dimensional probability graph into two-dimension. So this heat map is kind of showing you the density of a this model probability. Fine. Any question? Yes, no. You can type also, right?
So that prior posterior thing is like a 3D structure, no? Like which shows the probability density at
Right.
any. Okay.
Right. So now when I say that I need to choose a line from, I choose a line from that without seeing a data. So I will go by the posterior distribution. Posterior distribution shows me that the highest probability of picking is from this range. So I will pick a line and draw those lines. So it is not always I pick one point. I can take 10 different points because it's a distribution. So randomly 10 different points will be there, and I will draw them. So if I draw them, this is like this, right? Now what will happen? I see a data. So if somebody comes and give me a data, so you give me 1 point, right? So this is the blue point which is given to me, right? So this is a blue point that is given to me, only 1 point, right? So now in parametric space, if you want to draw the density as per this point, so this is what you need to be very careful here, right? So understand this graph. So I'm showing you this graph now, how to draw it, right? So this you will be doing in your lab. So now if somebody comes and give you only 1 point, this 1 point is having uh, this 1 point can define all those lines which are going near to this point, right? Because because I am adding some noise also, if you remember, for the data set which was taken by using beta distribution, right? So it means this point can define or can explain all those lines which are going near to this, like these lines are shown here in the figure. But if you see these lines, they can have intercept. So can you anybody tell me what is the range of the intercept if I want to draw a line which can explain this point? So what is the range of intercept? If this is a point, what is the range of the intercept, like which can from that intercept that line can go near to that point? Am I connected? Can you quickly guys tell me?
So like
Yes, sir.
zero intercept.
No.
Sir, infinite minus infinite, anything it contains.
Very nice. Can you repeat it, Yogendra?
From plus infinity to minus infinity. And
Very good. Very good. So it is minus infinity to plus infinity, right? So this is here like intuitively, you are here somewhere and I give you a point. So now if I give you a point, even you can start from minus infinity, but the slope will change accordingly, but you can draw that line and you can still go very near to this point. If you go from plus infinity, still you can start from this intercept and you can still go near to this point, right? Is this making sense to you guys? Yes or no? Quickly,
So
right? Type it.
in the data space, like the point is at y equal to zero, like close to y equal to zero.
No, no. Point can be anywhere, right?
Okay, so the value of x is between -1 to 1. The value of y is
You just think over it rather than just speaking too much. You should think over it.
okay.
So if I give you a point, then that just as Yogendra has said, as to define that point, you can draw a line from any intercept, right? So yeah, I can draw the intercept from here. I can draw from here. But just to make that line should go near to the point, I need to just change my slope accordingly, right? So the intercept ranges from minus infinity to plus infinity, right? And what is the range for my slope then? What is the range of my slope then? So it is also from minus infinity to plus infinity to accommodate it, right? Because if I am tracking intercept at minus infinity, then the slope should be plus infinity, right? Can you get it? Yes, exactly. Kawana as silicon, right? So just to accommodate it, what I have said, if there is a point somewhere in the space and you started from minus infinity, right? So this is somewhere minus infinity. So then if you started from minus infinity, what should be the slope? Can you type it? If I started from minus infinity, what should be the slope?
Infinite, sir.
Yeah, infinite, but there should, yeah, positive infinity. Why? The slope should be positive, right? If you start from here, the slope should be like this. Shantanu, isn't it?
Yes, yes.
Right? If I started from positive infinity, what is my slope? It should be negative infinity, right? Because I need to just accommodate it. Very nice. So it means the proportion that I will have is like this. So now if you see the density somewhere here, right? If you see the density for a given point, now this is just to make you understand how the plot can be drawn. Now I will fix to a point. So let's say this is a point. To explain this point, I can have a line which is having a zero intercept and zero slope, isn't it? So this is a line. So I will change a color for this. So just to explain this point, I can take a line which can have zero intercept, right, and zero slope, and it can go very near to the point. So this line can be possible or not for this particular point. So I am now fixing my point, right, as it is shown in blue. So for this particular line, can I have a line with zero intercept and zero slope, right? Okay, very good. So yes, I can have a 0 point. So in parametric space, if I draw it, will this point in a parametric space will have a higher probability or low probability? Tushar, can you unmute and let me know? For this point with zero intercept and zero slope, the probability of defining a point should be high or low? I think it just lost a connection. Anybody in the class?
High, because most of the lines are close to that point, like, passing through that region.
You can't say most of the point. I fixed the point right now. So point is fixed here.
So
So
most of the lines are
even you should not say most of the line, because I have fixed the line also, zero intercept and zero slope. So I'm specifically talking about a particular line and a particular point. So for this particular line, the probability is high, as Akash said, right? So this is high because this line is actually defining it. It is going very close to it. Now I take, so if I just draw this line into a parametric space, it will come where? Somewhere here, right? And all those points which is having a higher probability will fall into the this dark spectrum, right? So this is a dark spectrum. If you take any point, let's say I take this point. So what is the intercept here? What is the slope here? Slope is 1 and intercept is somewhere. It is minus 0.8, right? So if my intercept is 1 here and minus 8 slope is this, so this line is somewhere this, right? So for this particular line, the point is this particular point, right? If I choose this line, right? If I choose this point, so in this parametric space, this point is nothing. But what is the intercept? Intercept is 0.8 and my slope is what? Minus 1, right? So this point is having an intercept that is 0.8. So somewhere it is, this is having intercept is 0.8. So I should go to point. Okay, so this is 0.8. My intercept is, this is 0.8. Okay, I just taken the wrong side. So it is minus 0.8. So this line is not that line. So it is, okay, I will redo this thing. So just not to confuse. So I will take two examples just to give you intuitive. So I take first this point, right? So this point is, what is the intercept for this? The intercept is minus 0.8, right? And the slope is 1, right? So I go to the minus 0.8 and the slope is somewhere 1. I'm just making a sense to you guys, so it may not be very accurate what I am saying. So this is this line. So probably if you draw this line, it may be this line which is having some intercept at 0.8, minus 0.8, and slope is almost 1. If you choose this line, right? If you choose this line, this point, so then the intercept is somewhere 0.6, or zero point 0.7, let's say, and the slope is minus 0.8, right? So I am somewhere here, zero point 0.7 or zero point 0.8, and the slope is minus 0.8. So it goes opposite to it. So this point will corresponding to this line. Can you quickly write yes or no what I'm trying to show you here? Is it making sense to you? Like every point is having a higher probability in the from the spectrum. Very good. Very nice. Very good. So now this if you I am just drawing it. So the other catch here is, so if this column particularly, this particular figure, I am drawing just after seeing my data. No other information is given to me. I have seen my data only. So if I have seen my data, what is that estimation? If can anybody unmute and just let me know what is that estimation when I see only data and try to find out the value of the parameters? What is that estimation known as when I see only data, and then try to find out the value of my parameters? So when I see only data, this is known as maximum likelihood estimation, MLE estimation. And when you add prior information to that, I have taken a whole lecture on this. Please go through that slide lectures, right? Coin toss, when the prior information was added. That is known as map estimation, when you add prior information to it. So right now I am seeing only data. So it means what estimation is this? This is an MLE estimation, maximum likelihood estimation. So this column, which is shown here, is a likelihood column, and you need to find out which is that line, which is that point which is having at the maximum probability. So can you tell me any one point which is having a maximum probability? Can you find any one point from this particular figure? Is there any one point which is having a maximum probability? Yes or no?
All the points along that red dark line.
All the points, right? So there are infinite solution. So you cannot have a unique solution for this maximum likelihood estimation, because there are infinite line which is having a same probability of defining that point, right? That's good. Now, this is the probability which I see only when I see a data. And this is the probability which I had in my mind, right? Which I had in my mind before seeing any data. I want to combine these probabilities and to give a result to the new probability distribution, because there was a prior knowledge. Then I see a data. Using a data, I update my beliefs and I come up with some new probability distribution which will define my data as well as my prior information, which accommodate both the things. So here my prior says, so just to make you a whole understand, my prior says that I have some probability here, right, in this range. But my likelihood say I have a zero probability in this range. So effectively, the update will be that if I have a zero probability in likelihood, so it means I can never have a, so if I want to update it, then it will be nothing but at a combination of it. And if I just directly take a multiplication, I will tell you how I to take a multiplication, and then the resultant will be zero here, right? So then if you take directly the multiplication of these two, prior and likelihood, and it is not hard you to explain, right? Because the posterior, what it says, the probability over my parameters are nothing for a given data is nothing but the probability of a prior multiply the probability of a data given prior, that is nothing but likelihood, right? Data multiply by prior, or given a parameter upon probability of a data. So if I ignore probability of data right now, so this is nothing but a normalizer, which just scale the height of the density. So I ignore it. Then in numerator, the posterior will be nothing but the multiplication of likelihood and prior probabilities for every value of W. So if this is a grid, if this is a grid, right? So you take every value from the grid and you take the corresponding grid here on the likelihood, and you take the corresponding value from this grid and multiply them, and this will give define the new grid, which is nothing but the corresponding, remember it, corresponding product of the prior and the likelihood. And this is what you will get. And if you plot this heat map over it, this is what you got, right? This is what you finally got. Can you quickly write yes or no? If you have any question, please ask me. Can you write quickly yes or no if this makes sense to you?
So like, can we say like if we increase the points,
Uh-huh.
that prior curve will become small and small, like it's shown over there?
Yes, yes, I am coming to it. But till here, you have any question?
No, sir.
Okay, very nice. So I'm happy that most of the people have understood it. Very good. So now it is just like I am sitting somewhere on the road and I am finding out a probability where to get like a water or some other thing. So I'm getting a clues slowly and putting my updating my beliefs, right? So this was the first point when I see, and I updated my quickly my belief from this belief to this, right? I just updated my belief. So this will be acting as a new prior to me, right? So now this is my updated belief. Till I see a data, I always feel, till I see a new data, I always feel that this is the new distribution. The moment I see the next data point, the moment I see the next data point, I treat this as a prior to me, right? And for this point, I just draw a likelihood function, right? Likelihood graph, and this is my prior. I multiply them again, and this will give me the new posterior. This will give me the new posterior. Right or wrong? Yes or no? Can you quickly write? So every posterior will become the prior for the next step. Very nice. Very good. So this is all you need to understand in machine learning in Bayesian machine learning, right? So this is a very simple example, but a very powerful example to understand what is Bayesian learning, right? So in Bayesian learning, you start with some posterior, you see a data, you update your belief, and when you see a new data, you find out new likelihood function, you update your further belief, and further you see the data, you see the likelihood function, and you keep on updating your beliefs, right? So can anybody tell me, it's really a very catchy question before and winding up a lecture today. Can anybody tell me, and it needs a smart thinking, like you don't need to know a machine learning here. Why at this graph my probability just squeezed to a certain area? Why? Why in this particular graph my probability distribution is squeezed to a very small area?
If you increase the number of points, then the lines, the W0 and W1 gets limited, and because as you increase the number of points, the number of lines will be limited. Like you can't have an infinite range for both of these.
Anybody else?
So the range of W and W2 means decreases as point increases for
Right,
minimizing
right.
error.
My question is why to this particular point, why to this particular figure? There is a specific reason. The reason is because my true function is a line, and line can always be defined by 2 points. The moment you see the 2 points, you can have a better idea what could be the line, right? with some error. So if there was no error, what this graph will look like? If there was no error, what graph will look like? A point. Very good, Yukendra. Very good. Because I had introduced the error, so because of that error, it will not be a point, but it will be with little variance. With little variance, this is like this, right? Because I had some distribution, I had added some noise to that particular line, right? With that was a Gaussian noise, and because this Gaussian noise adding this spectrum here. So I hope that this figure makes sense to you now, and this is the best explanation which is given into a book. You can read through it. A lot of the things are not written by a author because he feels that you are smart enough, which you are actually, to go through this figure and make sense out of it. So please have a look over that section and read it, and we will further discuss over this figure again if you have any confusion. Thank you for today's class.